So we looked at Coulomb's law, with three charges, we looked at Coulomb's law in two dimensions, and every time we dealt with that, it was static electricity. In other words, they were charges that were not actively moving. What we're going to move to now are moving electrons, which is known as electricity, so current electricity where electrons are actively moving, not just jumping from one state to another. So we're going to be dealing a lot with circuits. I'm going to give you the notes that you need to understand what's going on in a circuit before we actually get to the circuits. So this is background information, and then we'll get to the circuits. I'm going to apologize in advance. This is a lot of notes. So we'll get started. So for moving charges, you've got a battery, and one side will be positive, one side will be negative. Electrons are going to build up on the negative side because, electrons have a negative charge, and they want to travel to the positive side. Why? Because they're attracted. But they need a path to do so. A complete circuit allows this to happen. So all a circuit is, it's a path for electrons to travel, and they want to go from the negative where they're all hanging out to the positive because they're attracted to positive. Voltage, also known as potential difference, so batteries are rated based off of their potential difference. You have like a 9-volt battery, 12-volt battery. Anytime you look at a battery, it's going to tell you the voltage between the positive and the negative terminals. So voltage is the improper term for potential difference. In other words, think about how much potential it has to go from positive to negative. So the more potential difference, the higher the voltage, because it's got more for it to be able to get there. Current represents the number of electrons flowing through a circuit. Current is measured in amperes, and the symbol for the ampere is an A, capital A. An ampere is a coulomb per second. It is impossible to have a high voltage but a low current, or vice versa. So in other words, the higher the current, the more electrons are moving, so the higher the voltage is going to be. So we've got voltage, we've got current, and the last thing we want to look at is resistance. Almost every object resists the movement of electrons. So there are things getting in the way of these electrons being able to move. It's the amount a particular object resists or opposes the current. Resistance is measured in, and everyone always loves this one, ohms. Like the yoga, Om. And the symbol is omega. Resistance depends on the material and the shape of the object. So a conductor will be a bad resistor because it's not going to really impede electrons as they're moving through. An insulator would be a good resistor because electrons are going to have a harder time getting through. But more specifically, the material or the shape of the object is what's going to determine the resistance. So putting this all together, current, voltage, and resistance are all related by Ohm's Law. And this is an equation. V equals IR. That's an I, not a 1. R is resistance. I is current. And V is voltage. So it's a really simple equation to use. V equals IR. You can rearrange to solve for current. So current equals V over R, and you can solve for resistance. Resistance equals V over I. I just always remember it as V equals IR. So two really simple practice problems. A typical 120 volt circuit in your house can handle a max of 15 amps. What is the resistance of the circuit? So we are given that the voltage is 120 volts And I probably should mention, going back up here, voltage, the symbol is V, the units are volts, and the symbol for the unit is also V. So this is the unit, and the symbol for voltage is V. So voltage is easy. The symbol and the unit are both V. The symbol for the current, I should have mentioned, is I, capital I, and the symbol for resistance is R. Okay, so given the voltage of 120 volts and the current of 15 amps, sorry, there's not more space. We want to find the resistance. Resistance equals voltage over current. Really, really simple. So 120 volts over 15 amps equals 8 ohms. Technically 8.0 with sig figs. And then just a second really, really simple example. A cell phone charger uses 12 volts. So we're given that the voltage is 12 volts. The resistance is 8 ohms. Find the current. Current equals V over R. So this is 12 volts divided by 8 ohms. 12 over 8 is 1.5 amps. 1 sig fig, approximately 2 amps. So Ohm's Law is very, very simple to use. We're not going to do anything as basic as this. We're going to be applying it to circuits. I'm going to keep on going, get through power, and then introduce what a circuit looks like. Okay, so now looking at power in circuits. Appliances are typically rated by the power that they use. Remember, the unit for power was watts. So you have like a 100-watt light bulb that's rating the power. And the symbol for power is still capital P, and the definition of power is still energy per time. So power depends on the energy of the electrons. So in other words, voltage is how much potential energy those electrons have and how many electrons there are. So the number of electrons is the current. So power depends on the voltage and the current in circuits. Directly related to both of those, power equals current times voltage. I always remember this as PIV. So V is voltage, I is current, P is power, and the unit for this is still watts. So it's still measured in watts. The symbol for the unit is still a capital W. Let's do these two practice problems quickly and then we'll get to the circuits. So a flashlight uses a 6-volt battery and has a resistance of 0.5 ohms. What is the power of the flashlight and how much energy does the flashlight use in 30 seconds? So here we're given the voltage is 6 volts. The resistance is 0.5 ohms. We're looking for the power and we're looking for the energy. How much is it using? So that's work. So power equals IV. We know that current equals V over R. So power equals V over R times V, or V squared over R. So power equals 6 volts squared divided by 0.5 ohms. This equals 36 divided by 0.5, so 72 watts. We also know from energy that power is work over time. So power times time equals work. 72 watts times 30 seconds equals the work. 72 times 30, 2160 joules. I'm out of room. I'll round up top. So coming up here, the power is about 70 watts. The work is about 2,000 joules. So pretty simple, again, to use these equations. And then this one I'll have more room for. Okay, this next one is similar. It tells us a certain air conditioner, it should say requires, not has, requires. Requires, get rid of that has. 6.25 amps of current on a 240 volt outlet. A more energy efficient model only requires 5.5 amps of current. How much energy is saved in 1 hour by the energy efficient models? So all we're doing here is figuring out how much power is used by the air conditioner versus the energy efficient model and then comparing the works. So power equals IV, this equals the current, 6.25 amps times the voltage, 240 volts. The power for the air conditioner is 1500 watts. Work equals power times time. Time needs to be in seconds. So the power is 1500 watts times 3600 seconds. That's the number of seconds in an hour. And this equals 540,000 joules. If we're looking at the energy efficient model, the power is 5.5 amps times 240 volts. And this is only 1320 watts. Work equals 1320 watts times 3600 seconds, and that's 4,752 joules. So how much energy is saved? We're taking 540,000 joules minus 475, 200 joules. And I made a mistake. This should be 5,400,000. And this comes out to 648,000 joules. So that's about how much energy you're saving by using the energy efficient model. All right, so we have power, current, voltage, resistance. All four of those things are going to apply to circuits. We're going to skip where it says complex circuits, and we're going to go over to where it says resistors in series. So we're going to cover resistors in series, resistors in parallel, and then that'll be basic circuits, and then we'll look at the more complex. So I apologize that this is out of order. We're going to skip complex circuits for right now. Skipping all this, and we're starting with resistors in series. So here's a circuit, just to introduce what it looks like. This is the battery. These are, in this case, light sources, and then these squiggly lines are resistors. So just to label the parts of a circuit, the squiggly line is a resistor. That is a battery. Batteries will always look like that. And then the lines are wires. So any other line is a wire. And that's the basic of what a circuit's going to look like. We're not going to be really looking at any of these. So your circuits will have the battery, the wire, and the resistor. And we're going to do probably like 50 different circuits. So you'll get really used to what these look like. So a series circuit looks like this. And all that means is that your resistors are next to each other. In a series circuit, the total resistance is equal to the sum of all the resistors. So the total resistance would equal the resistance of 1 plus the resistance of 2. All you're doing in a series is adding them up. When you have resistors in a series, the current is the same for all resistors, and the voltage gets split. So in other words, whatever my current is going through this circuit, it's going to be the same in these two resistors. My voltage will be equal to the sum of these two resistors. So this is going to take probably a couple times to get it, and circuits are essentially just giant puzzles. What you need to know about series right now is that to figure out the total resistance in the circuit, you add up the resistors. Okay, so let's do the example on the next slide. Find the total resistance of the circuit. Then find the voltage across each resistor and the current through each resistor. So, finding the total resistance. This is a series circuit because they're all in line next to each other. The total resistance equals R1 plus R2 plus R3. If it's not labeled, it doesn't matter what you call 1, 2, or 3. So this equals 3 ohms plus 1 ohm plus 2 ohms. 3 plus 1 plus 2 is equal to 6 ohms. So the total resistance in the circuit is 6 ohms. And whenever we do circuits, because there's going to be so many things that you're solving for, we're not going to worry about sig figs. So now we're looking for the voltage across each resistor and the current through each resistor. And in order to do this, we need to use Ohm's Law. The total voltage for the circuit is 12 volts. We need to figure out the current that goes through any of these. It should be the same. And then once we have the current, we can find the voltage through each of those. So we know in Ohm's Law that V equals IR. So voltage is equal to current times resistance. In order to figure out the current, you need to know the voltage. So knowing the total resistance, what we want to do is break the circuit down into a very, very simple circuit. So I call it, I guess, reducing the circuit. When we figured out what this was, in other words, the total resistance in series, you can redraw the circuit with one resistor, and that's equal to your 6 ohms. So in other words, this is your total resistance. And you've got your 12-volt battery. So knowing whatever the current is through the total resistance is going to give you the current through here, here, and here. So my total resistance is 6 ohms. My voltage through all of that 6 ohms is equal to 12 volts. So current is equal to resistance over voltage. Oops, I made a bad algebra mistake. Current is equal to voltage over resistance. Let's fix that. V over R. So this equals 12 volts over 6 ohms. 12 over 6 is 2 amps. So the current going through the total resistance is 2 amps, which means that since they're in series, these are all equal to 2 amps. So it's asking for the current and voltage through each of the 3 resistors. We know the current now. So current through all 3 of those, because they're in series, is equal to 2 amps. Okay, now we're looking for voltage. Ohm's Law tells us that voltage equals current times resistance. Well, we have the current and resistance for all 3 of those resistors. So for R1, 3 times 2 is 6 volts. For R2, 2 times 1 is 2 volts. And for R3, 2 times 2 is 4 volts. How do we check to know that this is right? These 3 voltages should add up to 12. 6 plus 2 plus 4 is equal to 12. These 3 currents, because they're in series, should be the same. And the rule's a little bit different in parallel, which is what we're going to look at next, and then I promise we're done. Okay, so parallel is easy for me to look at. It's a ladder. In other words, series is this, where they're all in line. Parallel, they're going to look like a ladder, so they're parallel to each other. So resistors in parallel. In parallel, the overall resistance is reduced. So the total resistance is found by taking 1 over the total equals 1 over R1 plus 1 over R2 plus keeps on going. So in other words, the reciprocal of the total resistance in parallel equals the reciprocal of all of the resistors added together. Parallel is the complete opposite of series. So for parallel, the voltage is the same and the overall current is split. So how we just up here had in series the same current but split voltage, in parallel we're going to have the same voltage but split current. So practice problem. We want to reduce the circuit. So reducing the circuit, you've got 3 resistors in parallel. This is going to be our total resistance and it's 12 volts. Anytime you're solving circuits, you want to get it down so that you only got one resistor, and that would be with your total resistance of the whole circuit. To find the equivalent total resistance, we're going to take 1 over 4 ohms plus 1 over 5 ohms plus 1 over 1 ohm. So a fourth plus a fifth plus 1, and then we're going to take the reciprocal of that answer. This comes out to 0.689, keeps on going ohms. So it asks for the total resistance in the circuit. My total resistance, again, we're not going to worry about sig figs here. It's about 0.7 ohms. So the 2 rules for resistors. The voltage is the same across all resistors in parallel, so that makes this easy. You have 12 volts here, which means that you're going to have 12 volts here, 12 volts here, and 12 volts here. So that's 12 volts, 12 volts, and 12 volts. It asks for the current in each resistor. We know that current equals voltage over resistance. So for R1, we have 12 divided by 4 is 3 amps. R2, we have 12 divided by 5. That's 2.4 amps. And R3, 12 divided by 1 is 12 amps. So for R1, current is equal to 3 amps. Voltage equals 12 volts. R2, current equals 2.4 amps. Voltage equals 12 volts. R3, current equals 12 amps. Voltage equals 12 volts. So how do we know if that's correct? Let's look at our reduced circuit. Our total resistance here was 0.68, kept on going ohms. Our total voltage through that was 12 volts. Current equals 12 volts over 0.68, keeps on going ohms, and this equals 17.4 amps. So 17.4 amps total of current going in here. Our rule tells us that the current is split between all of the resistors when they're in parallel, so that means that the current here, adding them together, should equal 17.4 amps. Well, 3 plus 2.4 is 5.4. 5.4 plus 12 is 17.4 amps. So this equals those added together. Our circuit makes sense. We're going to stop here. We're not going to make it more complex yet. I know this was a lot. We'll do practice. We'll make sure that we're understanding how this works with series and parallel separately, and then we'll combine them later.